you have something to look forward to. But in my opinion, it's the most useful, underused methodology out there. And with that, I turn it over to Linda.
Okay, thank you, Naomi. Thank you, Cameron, for keeping us straight here. So as Naomi said, this evening I'll be talking about displaying georeferenced or spatial data on maps. Now everyone thinks they understand data maps because they understand navigational maps, road maps, weather maps. And if they understand those maps, then they naturally must understand data maps. But I'm here to tell you that's not the case. Maps of data are much more complex than those other sorts of maps, and a poor design can lead the reader or viewer to incorrect conclusions about the patterns in the underlying data. And so I think it's our responsibility as developers, for those of you who are, to try to get this design right so that the easiest to interpret pattern from the map is the correct one. So I'll be talking, first we'll look at why map data at all. And I'll use some of the old cancer maps from the National Cancer Institute atlases to illustrate what we've learned from past maps. Then I'll describe the cognitive research program that we did on map design at the National Center for Health Statistics and show how the results from that program informed the design of the new NCHS atlas, new at the time. And then at the end, as Naomi said, I'll be extending map display to visual analytics, and we'll look at linked micromaps. So why map data at all? Many things vary by location: demographics, disease rates, behaviors, election results, all sorts of things. And just presenting a summary statistic masks these geographic differences. Now, in say the last 10 years or so, there's more and more data now available that has geographic identifiers on it. And mapping can now be done by anyone, even on your cell phone, not just by specialists using proprietary and expensive software. So now maps are everywhere. And the goal tonight is to make you a more informed consumer and perhaps developer of data maps. So the National Cancer Institute published 3 sets of cancer atlases from 1975 to 1999. And the National Center for Health Statistics published one in 1996, which we'll see examples from most of those. Prior to 1975, cancer statistics were published in tabular form like this. I don't expect you to read the details. The point is, this is only 1/4 of one of 700 pages. We refer to this as the phone book. It could be used as a doorstop. The sort order of all these cancer statistics was alphabetic. It's alphabetic by state and then alphabetic by county within state. There's no way to see any geographic patterns in this data. Now, it was good if you had a question of what is the rate in such and such a place. You could look that up just fine, but you couldn't judge patterns. So Tom Mason at the National Cancer Institute thought that it would be helpful to map these data. This was in the early 70s, and no agency except the weather people had any software to produce maps. So he had to go around the Beltway in Washington and use their facility to create these maps. First, I want to show you the legend of the map before we actually look at the full page. The rates were categorized by a combination of statistical significance, comparing each place's rate to the US rate, and whether it was in the highest decile of the 3,100 counties. So you see if we start, see if my cursor works here. Start at the top, the brightest red is both significantly higher than the US rate and in the highest decile. And then the 2 oranges are one or the other, but not both. And I'll skip down. White is significantly lower than the US rate. And this caused a problem. If there are any cartographers in the audience, you know that white usually represents missing data or none of the above, but here it was used to represent significantly lower. The none of the above was this green color. So there's no indication on this map of the level of the rate, only whether it's significant or not, or its reliability, except through statistical significance. For example, we think about New York City. New York City could have a rate that's only slightly higher than the US rate, but because of its very large population, it could very easily be significantly higher than the US rate. On the other hand, a rural area, say a county in Montana, might have very small numbers, but adding one case to its cancer count could easily double its rate because of small numbers. And that rate could be very high, but not statistically significant because of small numbers. So this map has its limitations. Let's see what it might have been good for. This is from that first atlas, 1975, lung cancer among white males. I've gone through the whole legend, but let's just focus on the red spots. They're significantly higher than the US lung cancer rate and in the highest decile of the 3,100 counties. You probably see right away, there's a geographic cluster in southern Louisiana. You probably don't see, there's also what I call an attribute cluster. The counties where those blue arrows are were port cities during World War II. And epidemiologic field studies, people mostly sent from NCI based on this map, went to all of these places shown by the arrows and found that a lot of men in those counties worked in the shipyard industry, shipbuilding and ship repair. And they were heavily exposed to asbestos in that work. And that was what was caused, that is what caused these high rates in those counties. Now, if you look around a little more, you might see this one county out here that's red in Montana, and you might think that's just random noise. One spot in the middle of low rate places. In fact, someone who knew the area looked at this map and they said, aha, I know what's there. That's the place where the Anaconda copper smelter used to be. So they sent a team of epidemiologists there and found, in fact, the smokestack there, which still is in place, it's a state park, I think. It's one of the highest smokestacks in the world. And it used to spew arsenic all over the community from this copper smelter. So the whole community was contaminated by arsenic. And the study found that that was the most likely reason for the hotspot here. Another important map coming from that first atlas was this oral cancer among white females. And you notice right away the colors have changed. That was a signal by the authors that they had changed the geographic unit. This is by state economic area, which is an aggregation of counties. The categorization of rates is exactly the same. The colors are different, but this bright red still means significantly high and in the highest decile. So you can see right away, there's this huge cluster in the southeast of high rates for oral cancer. At first, the epidemiologists at NCI thought this was probably due to an occupational or environmental exposure. Maybe they knew a lot of women in that area worked in the textile industry. Maybe somehow it was related to fiber inhalation or something. A grad student did her dissertation on this subject, did an epidemiologic study there, and found that no, it wasn't occupationally related. A lot of those women were dipping snuff, using smokeless tobacco. This was why the rates were high. It was their smokeless tobacco use. So this one map led to that study, which in turn led later on to maps banning the sale and use of smokeless tobacco by minors, and most recently to a ban of the use of smokeless tobacco by major league ball players, baseball players. So this had a lot of implications beyond the first publication of the map. I followed Tom Mason at the National Cancer Institute and had 10 more years of data to map. So I took that original 20 years of data and mapped by decade. This is oral cancer among white females again that we just looked at. I did change the colors. I kept the categorization the same, but I did change the colors. So now white does represent none of the above. Red is still high, and we see in the 50s, that cluster that we just saw on the aggregated 50s and 60s map. But when you look by decade, by 60s, that cluster was breaking up. And by the 70s, it was gone. By the 70s, the rates were high along the South Atlantic coast and the California coast. And by comparing this map, the 70s map, to maps, other maps in the atlas, we saw that this one looks very much like the white female lung cancer map. So we speculated that this change in patterns from the 50s to the 70s for oral cancer indicated that white women were changing their tobacco use from smokeless tobacco or snuff dipping back in time to more recently cigarette smoking. So this was one way we used these decade-specific maps. So reflecting on those couple sets of atlases that we had done, they were very successful at pointing epidemiologists to areas of high rates, areas that, because they were significantly high, they knew they had sufficient numbers of cases to study. NCI and then others sent teams of epidemiologists to do field studies in all those hotspots, so-called hotspots. And they found hundreds of important findings, over 100 publications following up on that first atlas. But as I've mentioned, we've gone through looking at these, there were a number of design issues. There's an inconsistent use of color across the atlases and even within atlas. It's difficult to identify a county rate or a spatial trend or clusters. The county's not in the highest 10% of rates and not significantly different from the US rate. We're all shaded one color, like green on that first map that we saw. So you can't judge the level of rates other than whether it was significantly high or low compared to the US rate. The rates in the highest decile and not significant might be based on small numbers of cases, as the Montana example I mentioned. And there's no level or indication of reliability. And finally, I mentioned already, white was used as a rate category when it's usually expected to mean missing data or none of the above. And finally, they used an aggregation of counties for rarer cancers, but state economic areas are not all contiguous aggregations of counties, and they're not familiar to most people. In fact, the Census Bureau no longer supports their definition. I was hired by the National Center for Health Statistics after doing that NCI atlas to do an atlas for them, because that's the agency that collects all the death certificate data from the states. I thought, well, I'll just poll some experts, ask what their advice is, as Naomi was talking about at that other study, and I'll just ask some experts and I'll do what they say. I'm not an expert in cartography. I got a different response from every expert. Nobody had the same idea of how we should design this atlas. So we thought, well, fortunately, my management provided a psychologist for us to borrow for looking at map design. They had a couple psychologists on staff there at NCHS who'd been working on survey design. So we started our own research program in map design. The research team included cognitive psychologists, few statisticians, and mostly under contract cartographers and geographers. Our target audience was epidemiologists. And to start, we got, I think it was 6 or 7 epidemiologists from NCHS in a conference room. That was our first focus group. And we pasted multiple maps all around the room, different styles. And we first asked, which map do you think you would like to use best? They picked, they voted. And then we talked about what questions did they want to ask of these maps. And they came up with these 3 general questions shown here. The simplest is location specific. If I put my finger on the map, what is the rate right there? Second, a little more complicated, what are the patterns on the map? Are there clusters there, or do I see an east-west trend? And then the most complex was comparing patterns across maps, like male to female or black to white. It was interesting that the focus group members changed their minds about their favorite map design after we forced them to try to use them to answer these questions. They came back and almost everyone said, I've changed my mind. The one that I thought I liked is harder to use than this one over here. So this was encouraging to us. We thought that that meant that it was possible maybe to come up with a better design, a consistent design that would allow the users to see the correct, the truthful patterns of the underlying data. So the cognitive experiments that we did followed standard scientific methods. We studied one map element at a time, and we held all the others constant. We randomized the order of maps shown, and we forced the volunteers to use maps to answer those 3 types of questions that they had come up with. And then we analyzed the percent error using logistic models by map characteristics. So before we got started, the psychologist who was working with us, Doug Herman, thought that it would be useful to help our thinking if he could come up with a model of cognitive processing for map reading. So he came up with this 3-step simple one, and he says that this isn't the only one by far that it could be proposed, but it was simple and it was helpful to us. First, the simplest task is to just perceive the information on the map. So printed or on the screen, that would normally be vision. We see what's in front of us. Second step, a little more complicated, is to comprehend the image and to store the information in our memory. So we might look back and forth between legend and map until we understand what we're seeing, and then try to remember all that, especially remember the legend, if not the entire map pattern. And then the most complex step is to integrate cognitive processes with our other knowledge to reason, find solutions, or communicate. Now you remember the Montana example that I showed for lung cancer. Someone looked at the map, they understood finally what the legend was telling them, and they said, I know what is happening there. They brought in their outside knowledge about environmental conditions in that area. So this is what's meant by that 3rd step. That's most complex. So as Doug said, using a lower level process is faster. So in this case, looking across these 3 steps, seeing is faster than thinking. And so the goal of our design is to reduce the cognitive burden on the user so that we're pushing the task that they're using to understand the map up higher in this 3 steps to have them use this simpler cognitive task. The aspects that impact design are perception, attention, and memory. So we'll come back to those 3. First thing we looked at was the basic type of map to use. The map in the upper left might look familiar to some of you. This is John Snow's cholera map from 1854 in London. Each dot represents one cholera case, and it's plotted at the residential address of the case. Below that, we have an isopleth map. And to create an isopleth map, there's an algorithm that tries to draw smooth lines around similarly valued places. It's like we see a hotspot here. To the right of that is a dot density map where the number of dots in any one geographic unit is proportional to the value it represents. Unfortunately, this kind of map is often misunderstood, and the viewer tends to think that each dot is a case in a specific place, like Snow's map was, and that's not what it means. There's another kind of map not shown here, a hexagon bin map that Dan Carr at George Mason likes to use, where you overlay a grid, in this case a hexagon bin-shaped grid over the map. You aggregate within each hexagon cell, and you map in that cell a representation of that aggregated rate. That works really well for removing aerial bias. I'll show an example of that in just a second. But the problem is with hexagon bin and these 3, dot, isopleth, and dot density, you need a much more precise location than we were able to get for death certificates or pretty much for any health outcome. The best we could get, the smallest unit we could get for death certificate data was county. And I was working in the agency that got this data, and I was not able to get anything smaller than county. So we were pushed pretty much to using a choropleth or area shaded map. And I mentioned aerial bias and use this. This is Maryland for those of you who don't know. This little burgundy square here is Baltimore City. It's the smallest of all of the counties plus city in Maryland. But about, I think, maybe 1 million people have lived there in that small area. Whereas some of these larger areas in the western part of the state have very few people living there. So this is aerial bias. Our eye is generally drawn to these larger areas, even though the small areas might have more people. So now we've decided to use choropleth maps, but the next decision was, would we class the rates or use an unclassed map? This is an example of an unclassed map. And it just means that in some way, the color is proportional to the value it represents. In this case, we have a light to dark in the red hue, and there's a greater saturation of color as we move to higher values. Now, if you look, pick a spot here in the legend, which is ordered, and we'll look, lost my cursor, look here, and we can see, if you have good color representation on your screen, you can see that this color is a little more saturated, a little darker than the one before. But out here on the map, where the colors are not ordered side by side, you have a hard time deciding what the value is. And so I've given you a question to answer here at the bottom. Does Texas have more people than California? It's very hard to tell. Those colors are very similar. So we decided for our atlas, we would use a classed choropleth map. The next thing we wanted to look at was color choice. What color scheme would we use? We did several studies of color. Cindy Brewer did most of the work here. And I understand that many of you have heard of Cindy. This was fortuitous. We were talking to Alan McAkron from the Department of Geography at Penn State. It's 1994. And we were at the point where we wanted to let some contracts for academics to do the research for us. And we were talking to Alan about some contracts, and we mentioned that we wanted to do something with color. And he said, I've just hired a person 2 weeks ago to work on color for us. And it was Cindy Brewer. She was in the process of moving from California to Penn State at the time. He brought her by to introduce her to us. She was a brand new assistant professor at Penn State. So she worked for us, and the rest, as they say, is history. She's now head of the department there. So we did a lot of papers together at the beginning. We found, just summarizing the color research, we found that the very distinct colors were best for rate readout. So that location-specific question of what is the rate right here? Think of a rainbow palette. It makes it easy when the colors are very distinctive to match up map color to legend color. We found that colors were preferred by our test group over grayscale, but there really was very little difference in the percent error. So if you have to use grayscale, it's okay, but they liked using color. We found that a color gradient was best for pattern recognition, looking for clusters or trends. And so what we ended up using was diverging or double-ended color scheme that combines these two. It combines two distinct hues plus a color gradient for each of those two hues. And we found that this was very good for looking for highs and lows. You could have one color represent higher than the average or middle rate, and the other hue representing the lower below that referent or middle rate. We also found that the accuracy of reading the accurate rate from the map or the correct clusters was best if you matched the user's expectations. For low to high values, that expectation is that you'll have a light to dark color or a cool to warm color. So if you switch those and have a cool color, say a blue, representing high, and a warm color like red representing low, I don't care how good your legend is, people make mistakes. So you need to pay attention to expectations. Also, you need to consider if there's a cultural meaning to your colors. In the United States, red is generally thought of as indicating danger or alarm or warning. Think of stoplights at the traffic lights. In China, though, it's a happy color. So if we were doing maps for a Chinese audience, maybe we wouldn't choose red for our hotspot color. An excellent source of information on your color choices for mapping is Color Brewer. Many of you maybe have already used this, but I wanted to show a demo here. So let me switch over. Let me show. There. I hope you all can see that now. It's set to sequential. Sorry, let me switch it. It was supposed to be set to a sequential color scheme with 5 categories. You could change the number of data classes up to 11. I think that's the maximum. And this is a simple light to dark scheme. Let me change it to qualitatives. I lost my qualitative. Okay, there's one. Think of this. Oh, I know. I have colorblind safe click. That's a mistake. Let's go back to 5. I was playing before we started. There's a 5 category qualitative color scheme. So each color is very distinct from the others. It's very easy to read these off the map. What's shown on the right is just a dummy map, a sample, so you can see what it might look like when they're arrayed together. You can turn on showing roadways or cities. You can change the colors of either of those. And here we see that doesn't look bad. But if I chose a different color scheme, now the roadways disappear over the red value ones. So you can play around with that and see which one works for your favorite color scheme. So let me turn off roads and cities. And now let me look at a diverging scheme. Now you see here, with I think there are nine choices shown here. They all have a neutral color in the middle, and this is where your referent color or referent rate or value would be. And in the one that I've shown here, the browns would represent values above that referent, and the blue-greens would represent values below that referent. Within the browns or within the greens, we only have 2 shades to remember, the 2 browns, 2 greens. So it's very easy to remember. If you want to look at the big picture on the map, you need only look for one color at a time. So where are all the browns or where are all the blue-greens? We can click over here that look at the colorblind safe color schemes. If I click on that and unclick it, there are 3 on the right that disappear. So those 3 were too much red-green. So a colorblind person, and the most common type is red-green blindness, they couldn't see those, but they probably are okay using a map with these 6 color schemes. So once you've decided on what you want, you can look over here and you get the exact definition of those colors in one of several different definitions, RGB or hex or whatever. So this is a very good tool for deciding on your colors. Oops, I have to go back to my slides. Trying to change that. So the next thing we looked at was reliability representation. We did 2 studies on this topic, and some of the test maps are shown here. You can blank the unreliable places, shown in white. You can have a separate map for rate and reliability, put them side by side. You can use a bivariate color scheme where the color for the rate, the categorical rate color, has a saturation that's diminished if it's unreliable. You can see, for example, there's a pink county here in Montana. You'd look on the legend and see that that's in the reddish category, but the pink, the lightened color, means it's not a reliable rate. Or you can hatch the unreliable places in such a way that the rate color still shows through. So you could judge patterns and clusters by looking at color, but for the rate readout question, putting your finger on the map, you would be warned that that rate is unreliable. So we found that blanking out unreliable rates like this on this map hampers cluster identification. So we don't recommend that. You can't tell if the pattern continues across the blanked out areas. We found that map pairs and hatching worked significantly better than the bivariate color scheme. And our resident psychologists thought that was because the user has to remember twice as many colors from the legend as on any of the others. And so there's just more to remember. That wasn't me, it did it by itself. So the bottom line here for these, after these several studies, was that reliability can be indicated on a map with minimal impact on several types of tasks, several questions you might ask of the map. So the next thing we looked at was comparing maps in series. And Cindy Brewer worked with us to do a study looking at what kind of legend would be best. And we found that the accuracy of comparing maps in series was significantly better if they all had the same legend, a common legend, the same categorization. And you might now, years later, you might go, well, sure. Why did you bother doing that? Well, nobody had shown that. There was an opinion, certainly, that that would work best, but nobody had shown that. And so while we were testing other things, we thought, well, we'll just check this. And I would have been really worried if we had not found a difference. So it was significantly better with a common legend. So the three ways of showing maps in series. First, animation. It's good for smoothly changing patterns. It's not so good if you have pop-up hotspots like we did with our lung cancer map, things that are not clustered together. Second way is to show the maps side by side or on small multiples on the same page or on the same screen. And the third way is to just map the differences between pairs of maps. You remember our little cognitive process model that we had? The simplest thing to do was just to see what was on the map, not have to think much about it. And this leads us to mapping the differences directly. Well, let's look at some examples of these. Here's a weather map, animated, and you should see clearly there's a large weather pattern, storm system moving across Maine. It's a large block of bright colors. It's contiguous, and it's moving very smoothly. You might not have noticed there's some pop-up showers in Western New York. Your eye was probably drawn to that big storm in the Northeast. So let's look at a different kind of data. We're moving to more contemporary data now. The Washington Post published maps showing the month where each US county reached its peak number of coronavirus cases. Now, this is just a binary map. I'll show a map for each month from March to November, and each county is shaded once on the map for the month in which it had its peak number of cases, and it's not shaded at all in the other maps. So let's look at this. Now, other than noticing that most of the counties peaked in the latest period in early November, could you see your hometown and when that peaked, or your favorite county, when did that peak, if not here? Probably not. This was just a binary map. So, and the animation was slow. So what was the problem here? Well, the problem was attention and memory and the impact on animation. Our attention span is limited. Our brains can only attend to or pay attention to 3 or 4 items at once. And the psychologists talk about a couple types of blindness that are relevant here. One is attentional blindness. you're looking at the wrong part of the image. Your attention is at the wrong spot. If you're looking at the East Coast and the action is all on the West Coast, you won't see it. And your attention is drawn away by movement. Think of those dancing hamsters that pop up on your websites when you're looking around. There's a reason they're moving. Your attention is also drawn by saturated colors and large objects. Second type of blindness is change blindness. It has to do with our memory. The first image is mentally erased before the second image is seen, either because it's too complex or there's something in the middle or the animation is too slow. So you don't see the differences. You can't remember that complex map that was just before. So these cognitive limitations really impact showing maps in series, in particular animation. So this is how the Washington Post published these maps originally. They didn't animate. They were published on one page. Now you can look around and find your hometown or find your favorite county, and you'll see which month they had their peak of coronavirus cases. It's much easier this way. So let's look at another series of maps. It's a little more complicated. It's more than a binary map. We have multiple categories of color, categorization of the values being mapped. This is cervical cancer mortality rates over a 45-year period mapped by 5-year blocks. Small multiples, all using the same categorized legend, same categorization and color coding of rates. Now, this can be a real problem. This kind of display with a common legend, small multiples with a common legend, can be a problem if you have an extreme range of rates or values shown across your maps. And that's the case here for cervical cancer. The rates dropped a lot from the early 50s to the early 90s, to the point where most of the areas in the earlier maps are shaded by the same color, deep red. And most of the areas in the latest maps are shaded, almost all shaded in the same color, blue. So we have no way of distinguishing within that one color how high or low the rates are. So these are not good for that rate readout kind of task where you put your finger on the map and say, what's the rate there? They're very good for showing, in this case, how rapidly the cervical cancer rates declined. And if you had a few minutes to look at these, you might see where there's a cluster of areas that declined less rapidly. So let's look at another type of maps in series. I wanted to compare patterns not across time, but across all 17 causes of death shown in that NCHS atlas. I wanted to look and see if the map patterns were similar across some of the causes of death. Well, I had the same problem as we saw in the cervical cancer series, a very wide range of rates from the rarest cause to the most common cause. So what I did, I used a comparative mortality ratio, and that's just scaling the rates. I divided the age-adjusted rate in each place by the US rate for that particular cause of death. It's called comparative mortality ratio. So now we have a relative scale going from light to dark. We have the lightest, light blue is, oops, this, if I barely touch it, it changes. The lightest blue is a place that has a rate less than 75% of the US rate, up to the highest, which is the darkest color, and those rates are more than 25% higher than the US rate. So it's a relative scale. And if you looked a little bit, you'd probably see that some of these causes of death had very similar patterns. Now moving on to the third way of showing maps in series is just by mapping the differences. This is another Dan Carr design called comparative micromaps. And here he's shown in the top row maps over time. I didn't bother with the legend or anything. It's maps showing values over time by some color categorization. Below that, in the second row, he's showing by some categorization what the difference actually is. So the idea is this offset in location by this map should intuitively tell the reader that this map here has something to do with these two maps above. You could show a difference, a subtraction, a ratio. Here he's shown what's the new color if it changed. So we see here Nevada was in the gray color. In the second period, it's in the red color. So the difference map shows red. Whereas California didn't change from gray to gray, so it's not shaded in the difference map down here. So there are a number of ways you can represent difference, but the point is the reader just looks at the differences directly and doesn't have to do any computation mentally. So based on all that research, here's our map design recommendations summarized. You should design for particular audience and purpose. For our rate maps, the quantile categorized choropleth or area shaded map worked very well. Boundaries I didn't talk about, but they should be smooth enough and thin enough, the lines, boundary lines, thin enough to let the color show through, but detailed enough to show important features like lakes and bays. You have to decide for your purposes, do you want to show lakes and bays like the Chesapeake Bay in Maryland, or do you want to just smooth over that? The colors should be consistent across the maps in the atlas, if that's what you're doing. Colors should be chosen for the visually impaired, and they should be consistent with color conventions, whatever they are. Rarely can a single map do everything. Let's see. We should identify unreliable rates by hatching, so don't blank them out. And map comparisons definitely require common legend across maps, and you should show maps side by side or display map differences. Rarely will animation work unless you have a weather type map. Multiple maps are often needed to address different questions, to focus attention on different scales, or to compare modeled versus observed rates and other things like that. So we applied those recommendations to the new, at the time, new NCHS Atlas for 17 major causes of death. It was a 2-page design, as you see here. So we have multiple maps to answer different questions. The top page was a full-page map of the age-adjusted rates. It's a classed choropleth map with quantile categories. Let's see. The colors are usable by the visually impaired. You probably recognize this color scheme from my earlier color brewer example. Unreliable rate areas are hatched. You might not be able to see it here, but if you're looking for clusters or other spatial patterns, trends, you can look for only greens or only browns and see clusters there. But if you have a rate readout question, put your finger on that map, the hatch will warn you that that rate is unreliable and due to small numbers. We have a standard vertical legend. And on the second map, we have a couple of smaller maps. This red and blue one is using the standard colors for a significance map that we had used in a prior atlas. So we thought that would be kind of intuitive for people who had a question about, well, what I saw on that blue, green, and brown map, was that a significant one compared to the US rate? That is answered here. Below that, there are 2 age-specific maps from model estimates. And above that is a graph of regional rates for those same 2 age groups. And the graph and these 2 maps are linked by a color bar. So this atlas won an award as the best illustrated government publication in 1997. And I think it's due to all the work that we put into it over several years to study how people read information off maps. So these have all been pretty old maps that we've been looking at. So let's look at more contemporary data and maps and see if the newer maps, the maps you might see today, are following these recommendations or not. And just as a reminder, here are the 3 types of questions we think people want to ask of a map. What's the rate right here? What's the pattern on one map? Or how do patterns compare across maps? And as I said before, rarely can a single map answer all of these. So let's look at some election results to see how the question you want the viewer to answer drives the map design. All of these election results I downloaded the day after the election, so not all states had called their results yet. This is from the Wall Street Journal, standard US state map. The colors are consistent with common use, so red for Republican, blue for Democrat, and it's showing us the winner of the popular vote by state. The journal has added in a little extra information for the states that hadn't been called yet. We see by a lightened color which way they were leaning. So Nevada was leaning Democrat on the 4th. Georgia was leaning Republican on the 4th. It later changed, but you see that it hasn't been called by the lighter color, but you see which way it's leaning by what that color is. Now, I've mentioned aerial bias a couple times. Your eye was probably not drawn to Rhode Island, this tiny place over here. It was probably drawn to one of these big red areas like Montana. In fact, we know that Rhode Island has a greater population than Montana, but you wouldn't know it looking at this map. This is aerial bias. This design is very good for showing you who won the popular vote by state, but that's not how we elect our president. So it's not the most relevant question to ask, probably. So the Wall Street Journal published multiple maps, again, for multiple questions. Here's their cartogram showing the electoral vote results. Now every state is made up, is some shape made to look like its real shape, but it's made up of small squares, and each square, each block represents one electoral vote. So let's look at Montana and Rhode Island again. Here's Montana. Over here, it's very small now. It only has 3 blocks in it. It only has 3 electoral votes. Whereas if we look over here at Rhode Island is bigger with 4 electoral votes. So now our visual impression by area is correct relative to the number of electoral votes. The cartograms in general are good for removing aerial bias because the area that you see is in some way proportional to the value that you're trying to display. It can't always retain the correct shape, orientation, and neighbors that the original map had. So they've done a good job here of trying to make each state the shape that it really is. So here's New York, and you see there's Long Island they've stuck out here. That's pretty good. But over here, here's Washington State, and it looks like there's no eastern neighbors. Idaho is down here. So you can't do everything with these cartograms usually. The New York Times did a similar map, but they've improved on it. They just added a little bit of white space between the states, not enough to interfere with looking for patterns and clusters and trends, but you can see better, I think, the shape of each state. You can see the outline of the US looks familiar. It's not squished. And it does a better job, of retaining the neighbors and contiguity of state to state. So by not forcing the states to be jammed together like a jigsaw puzzle, they're better able to keep the relationships among the states. So we look at Washington State. Here's its neighbor, Idaho, as it really is next door. The New York Times drilled down to look at the popular vote by county. Let's zoom in a little bit so we can see better. They've used the same colors, red for Trump, blue for Biden, that would be expected. the circle size now for each county is proportional to the amount each county's leading candidate is ahead. And if you were to look at the entire US map, I think there's a striking urban-rural difference here by party. And let's just look, oops, let's look at Atlanta. Atlanta is all these blue circles here in the metro area. They all went for Biden, they're blue, whereas the rest of Georgia pretty much went for Trump. So we can see that by drilling down with these circles. Now, question naturally would come up, how does this differ from 2016? And Times, again, multiple maps for multiple questions, they showed a difference map, 2016 to 2020. And we'll zoom in so we can see this a little better. They used what we call a redundant coding for the legend. There's blue for Democrat, red for more Republican, but we also have a difference in the direction of the arrow. So if we were to photocopy this map into a grayscale or black and white, we could still look for clusters and patterns by the direction of the arrows. We don't really need the color, although it's easier. We can see here more easily by color that there's a cluster of counties in Northern Virginia that changed and were now more Democratic than they were in the previous election. And back again. And we looked at Atlanta in the last map. Let's look at this now, looking at change. The core of Atlanta is gray. That means it didn't change. It went Democratic before, it went Democratic this time. But look at this ring of counties around the core of Atlanta. And now they all changed to Democratic leaning. They voted Democratic, whereas they were voting Republican before. And so this ring around Atlanta is probably why all of Georgia ended up going Democratic. Its electoral votes went Democratic. But you can see that on this map pretty easily. The Washington Post went a little beyond that. Similar to the Times map that we just saw, they're using color, red for Republican, blue for Democrat, direction also showing Democrat or Republican in difference since 2016. The length of the line also means the change in the winning margin. So far, we're okay. But then I noticed, one more thing. They have another variable, a change in turnout is indicated by the angle of these lines. So an angle more looking upwards is a greater change in turnout in that county for 2020 compared to 2016. Now, if you look, most of them are showing a higher turnout this time. So, okay, so far, but then I saw there were these lines. I didn't see anything on the legend that explained why there were multiple lines per county. And I didn't notice that at first, but when I looked at Delaware, I know Delaware only has 3 counties, and there are many more than 3 lines there. So I couldn't figure this out. I wrote to the author, who turns out to be the editor, and he said, oh, those are showing population density. So you can tell the more lines, the more population there is in that county. So, okay, but the legend didn't say that. And if you look at the online version, these lines are waving. It looks like seagrass. So, no, don't do that. In the email explaining those lines, the editor said, and I also wanted to show an indicator of urban-rural status for each county, but I just couldn't figure out how to get that into this map. And my mind almost exploded. No, this takes multiple maps. This was way too complicated. This already is showing 4 variables on this one map, and he was trying to get a 5th in there. No. If the reader doesn't understand your map quickly, they'll quit. They won't write to the author like I did. And when they quit, you've lost an opportunity to communicate your message. So your map has to be the simplest and the most accurate for representing the underlying data. So what the editor / author of that map was trying to do was visual analytics. He was trying to look for some factors about the counties that might suggest the reason that they voted one way or the other. And as Naomi said in the introduction, linked micromaps are a good way to do that. And these are Dan Carr design. Dan's at George Mason University. Let's see, time out. So the linked micromaps, it's a design that links a series of small maps with columns of statistical graphics by color. The rows are sortable by geographic name or any statistical column. They were originally designed to map only US states, but now they've been expanded to several countries and several states, US states by county within the state. Default layout is usually pretty good. It gives publishable output, we think. And we've expanded the types of graphics that are included. It used to be just dots and dots with confidence intervals and so on, but now there are lots of other glyphs, more than are shown here. The examples that I'll show now were all implemented by Micromap ST, the package that we developed in R. So here's a basic layout, a simple layout to illustrate the design. We have columns that include the area name, ranks, age-adjusted rates, or some graphic here, and a column of maps. The rows represent the geographic areas, in this case states, and the colors link across in one row, link the columns across in one row. So here we see the first one, North Dakota, is represented by red. That's like a legend dot. The rank is 1. The color red on this panel shows you that goes with North Dakota, it's red. And that's pretty obvious because it's all in the same row. When we get over to the map, they're not lined up by row. So we see that the red here is telling us where North Dakota is on this little map. So we can read across and see by color what's what. The color now is not implying a value. It's merely a way to read across the row and find that place on the little map. You'll also notice that the states are grouped here in groups of 4. So 4 or 5 is typically what we use. Call these perceptual groups. These groups allow the user to just focus on only 4 or 5 states at a time, to look at little chunks of this graphic. It simplifies the cognitive tasks that they have to do, and it allows us to reuse color. So you see here, red is North Dakota in that grouping, and it's Wisconsin in this one, and it's Illinois in this one. So that's okay because the reader is using one grouping at a time. So let's move on. There are other designs other than states. We've expanded this package to show counties within a state, user-defined administrative areas like Kentucky, administrative, I don't remember what they're called. Anyway, administrative areas, areas within a city as Seoul, Korea, and provinces within a country as China. We're working on ways to more easily import your own geographies. I'll mention that in a minute. So this is the linked micromap design for knowing someone with COVID. This is very recent data. Carnegie Mellon is conducting, starting in September, a survey through Facebook to see who has had COVID, who knows someone with COVID, other COVID-related questions. So So in this case, we'll walk through the design again. We've turned the columns around. The map is on the left. This is just sorted alphabetically by state postal code. So Alaska's at the top. It happens to be red in this color scheme, 5 grouped at a time. We see where Alaska is. Of course, it's a pullout. And there's Alaska. And we see that its value is red. What I'm showing here is a percent who knew someone who had COVID on November 9th in this Facebook survey. So we can look at this, and I don't see much of a pattern at all. It's alphabetic. So before I move on, it clicked early, but there it is. This is the R code. If you're familiar with R, this is the R code that you would need to create this using Micromap ST, our package. There's a panel description where you describe what you want in each column. So maps first and then so on. And then the second call, actual call to the package, telling it what you want to see. So this defines the content. So that's not very useful to look at it alphabetically. Now we've sorted by this percent knowing someone with COVID. And we're looking at November 9th, a recent date, sorted in descending order by state. And now we can see we have a geographic cluster. The highest 5% knowing someone who has COVID are all clustered together around the Dakotas. We can see that in the second panel, the second grouping, we have a different 5 colored states. They happen to be contiguous to the first 5. And so we're looking for accumulation down these maps. So the first 5 from around the Dakotas are represented on the second map as just yellow shaded, which is saying we were already shaded above. But the 5 that are shaded here are in the colors that you can read across and judge what the values are. And so we can go down all the way through the top half of the states. And looking at the top half, we see that the coastal states are not included. So the top half are in the central part of the country. And the coastal west and east coast states are lower in value for percent knowing someone who had COVID. All we did to create this was add a sort variable at the bottom of the call, saying we want to sort in descending order by percent knowing someone. Now that we see patterns, we can start to explore factors that might be related to them. For example, percent who usually wore a mask. When we asked it, when Carnegie Mellon, when they asked in September, we chose a date far enough back in time that the occurrence of COVID wasn't impacting whether they were wearing the mask or not. So this was a couple of months before. So everything is the same, map's the same, the color coding's the same, this column of knowing someone with COVID is the same. So now we just have this extra column of usually wore a mask in September when the question was asked then. So we've not sorted on this wearing a mask variable. It's just still sorted in descending order, percent knowing someone on November 9th who had COVID. So if you take the long view here and look at this pattern, I think you can see an inverted V. And what this means is that the states that have the highest percent of people who know someone with COVID now in November, or at the time in November, they were states that had the lowest percentage of people wearing a mask in September. So we get this inverted V shape. We found that let's see. Oh, sorry, I'll show you this first. The only thing we had to add to the R code, to the function call, was to ask for this extra column on the right. So asking for a dot plot percent who wore a, sorry, it just keeps jumping, who wore a mask, and give it a label. So we found that this linked micromap design is useful for exploration as well as for communicating the information from model results. Now for micromaps implementation, just a second here. For the implementation, there's micromap ST, the one we developed that's on CRAN, our package. Micromap, which without the ST, which was developed by the EPA as an R package, also on CRAN. There's Shiny apps now shown here. There's there was a SAS blog post that shows how to do it in SAS. Adobe Illustrator shows, I think it was a difficult to create illustration in Adobe Illustrator. I wouldn't want to have to use that all the time, but it worked. And there's LM Shape Maker, which isn't quite out yet, but it's a Shiny R package that will modify your shape files for use in linked micromaps. And I've shown you their website that you can read about that there. So here are the references grouped by the topics that I covered. So the Atlas references at the beginning, and I've only shown 2 references to our own work, sorry, summarizing the cognitive research relevant to map design. And I do that because the work that we did that I showed earlier, say with Cindy Brewer and Alan McAkron and all of those people, the publications are scattered across the literature in cartography, statistics, different types of journals. And so in our in the book Visualizing Data Patterns with Micromaps, we've pulled all these together. And in a paper I did in 2009, I have all the references in one place there, so you can find what you need there. Chapter 2 in our book is summarizes all of this work, plus brings in all the relevant literature from others, like from cognitive psychology and all, such as by Bill Cleveland. Let's see, what else do I want to point to here? If you're interested in the R packages, this issue of Journal of Statistical Software in 2015 has back-to-back articles by our group talking about Micromap ST and the EPA group talking about Micromap. So you get examples and text around the code that can help you out. And finally, some of my favorite authors here. I've given you some general references looking at that we used and for looking at showing maps by micromaps, some of the background behind that. So with that, I will stop talking. So, who was asking for questions?
One moment. Naomi, I think you're muted.
If anyone has a question, you can either ask in the chat box to be unmuted or type your question in the chat box. Linda, there's a question whether the ST stands in Micromap ST stands for state, as in US state?
Yes. Let's see, I'm not muted, am I? Yes, it does. And our first implementation was only for states. And we knew that the EPA group was working on micromap without any qualifier. And so we just put ST on ours to indicate states. Well, now it's working against us because we've moved beyond states, but we didn't want to change the name.
Great, thank you. So next we have a question from Abe.
Thanks. Yeah, thank you, Linda, for this amazing talk. Definitely, this is the first time I'm learning about linked micromaps, so I appreciate that. I wanted to ask you your thoughts about using this paradigm for visualizations that aren't geographical in nature. So using the linked micromap concept, but maybe replacing the geography with some other kind of visualization that's broken down into pieces the way that your maps were. Have you seen anything like that? And if so, what are your thoughts on that?
Well, it's overkill to use it if there's no geography at all. But we do have an example in our book showing the baseball diamond and where each player normally would stand, and talking about showing statistics by position of the player on the field. So it's still geography because it's a location on the baseball field, but it's not the usual geography that I've been talking about here, US geography and so on. So there ought to be some location involved that's of interest, or this is probably overkill. It doesn't have to be on a geographic map. It could be something else. I've seen test runs where the location was the location on a body. So there was a diagram of a person, you know, and you could look for correlations where things were clustered, like a tumor was typically clustered in this spot versus that spot. So it doesn't have to be geography of the land. It could be geography of something else, locations of something else.
Great question. Thank you, Abe. So next we have a question from Mark.
Hey, thanks, Cameron. Linda, wow, I'm sure I speak for almost everyone on the call. Your presentation was just chock full of interesting stuff. My mind is completely full. I particularly like that you gave some names to things that I know, but didn't know what to call them. So you talked about aerial bias. I definitely know about that, but I've never heard someone just put a label on it. You also talked about redundant coding, which is what I want to ask my question about. And I think it relates potentially to the perceptual model, which I'm so glad you shared that, which is just really interesting to think about. So I've used redundant coding, as probably most of us have. And sometimes I'll just apply it and I'll say, okay, it works in this instance, it doesn't work in this instance. But it's not often been clear to me why it works in some instances and not others. And I'm thinking it probably has something to do with this perceptual model. And since you're a more experienced person, I'm wondering if you kind of know, if you can articulate situations where redundant coding works and doesn't work so well.
If you use something, say a hatch pattern for your second way of showing, say, let's talk about rates.
Yeah.
It can be too busy, or if your lines are too thick, that second way of encoding the underlying number can interfere with seeing what the other one is showing. So in other words, if I have a very complex hatch pattern, or my hatching lines are too thick, it'll make it hard to see the color that's underneath. And whereas you thought you had a redundant coding of hatch pattern and color, the one might overlay the other or interfere with judging the other. That's one example.
Yeah. Okay, great.
But you need to try it.
Yeah, I mean, that's what I find. But that,
Yeah.
you know, but I really do like the perceptual model because that you gave, because I absolutely agree. Like, it's easier just to try it, but it is also interesting to know why that is, you know, and I think it can help. So thanks a lot for that.
So I think the busyness of the graphic of the map that you're looking at can interfere, regardless of why it looks busy. You know, is it too many lines or too many different colors, whatever it is. If it's too busy, people won't work too hard to understand it. And that's what we found with that Washington Post map.
Which I agree with.
Difficult. People just go, I don't know, and they turn the page.
Yeah.
You don't want that. You want to make it as easy as possible, which is why I like these later maps where they're not requiring you to remember all the maps in a series, you know, automated series.
Yeah. Thanks so much.
Let's map the difference directly.
Great. Thank you, Mark. So we have another question from the chat. Someone was wondering if with this package, they can bring any shape file they would like to the multi-maps.
Any shape file.
Or what are the limitations?
There are limitations of what's in there right now. We're working on having it be able to use other shape files. You can bring a shape file in, but you have to have it smooth in the way that it works for those very small maps. So that's why we've been adding different shape files that you could call. And I showed the ones like for China, and in that slide. Eventually, when that, what was it called? The LM Shape Maker. When that's out, and I should say the problem is the person who did that graduated and never quite released it, but I've been assured that it will come out soon. So that would allow you, that LM Shape Maker would allow you to modify your own shapes so that they would work in Micromap ST. Then you can map whatever you want. Right now, today, you can't quite. It has to be something that we've developed boundaries for, appropriate boundaries for.
That makes sense. And I realize I misasked the question. It was specifically about LM ShapeMaker, but Kat, it looks like that you answered it.
Okay.
That's great. So I have a question. I was curious about now that since many of these maps can be consumed on screens and people can have things like tooltips or click and interact with things, whether if you have thoughts about what sorts of things people might want to do when they're able to take advantage of interactivity when working with a linked micromap.
Right. All atlases today are interactive. So you could go to, I haven't looked lately, but I think you can still go to the CDC website and find maps of for mortality maps. Let's see. I think the principles are the same. If you're just going to a computer presentation rather than printing, I think the principles that we found would be the same for creating the most usable and informative kind of maps. So, maybe that didn't answer your question. Ask a follow-up if that didn't answer your question.
I guess like when we think about overload, would you think about like putting additional graphics inside a tooltip, or try and keep it light and limit to numbers or things that aren't as visually intensive? I guess it varies based on the question, but.
you could have a tooltip that would pop up with the value that's being mapped there. That might be useful. But if you start putting too much in that tooltip, I think it can overwhelm the user. They're getting too much. You can always have something pop up below, like if you're highlighting on the map, and I can't remember where I saw this now, but the top part, so you see my hands, the top part of the screen had the map, and then below that was some detail about whatever was highlighted above. Now, if you were using that kind of design, then you could have more information on the bottom. You could have the rate that was color coded above, but maybe more information, the population, the actual rate, the confidence interval, what other things, but you'd only look one spot at a time. That could be done.
That makes great sense. That sounds like the cross highlighting pattern that we see on some dashboards. So thank you.
Right.
So it looks like Mark has another question.
Hi again, Linda. I also wanted to ask you about the micromaps example that you showed, the COVID by state. You know, I do find that sometimes with a novel presentation, you know, that it's like sometimes what I'm not sure if it works. You know, it can work after I kind of digest it a little bit, but there are a couple choices I was curious about, and I wanted to kind of get your thoughts about. One was I wasn't so sure that the use of like, you know, the changing like color legend for each group of states, right? That they're like, one state is red, another state is purple, et cetera. I didn't know, to be honest, if like that added value or subtracted value. I sort of feel like with states, people, you know, kind of have a pretty good idea of like where they are, right? And so, but you know, again, maybe I'm not seeing something, so I'd be curious about that. And kind of similar to that, you know, the fact that as you went down, that the states that had been previously highlighted were then coded in yellow and outlined. Again, I wasn't sure if that added value or more, you know, ink that was kind of not so much confusing, but I didn't need to see it. But you know, but you're so, I mean, this has so much thought in it that I feel like you must have a reason for those things. That's what I was curious about.
Yeah, so I don't know. Can you still see my slides?
Yes.
Oh, okay. Let me back up to the.
Yeah, this is, yeah, exactly.
Oh, so there's one.
Yeah.
You might know where every single state is, but I confess I've been working with maps for decades and I make mistakes. I'm not quite sure, you know, is that Idaho, is it Montana or what? So I don't agree that we don't need the color.
Well, it wasn't so much here, but once you had sorted them.
Okay, we'll sort them.
Right.
Okay. Still, it's helpful to be able to read the color across, because in that, I don't know, I hope you can still see my arrow. When you read across to the value on that part of the on the micromaps, you need the color to tie into the map.
You know, and you know what's really interesting about us having this conversation is it's actually, I think it's an example of redundant coding. Right, that the color is representing something that is also represented in a map and represented by a row. And yeah. I think this is where I'm saying like, I'm not sure that this works for me. But you know, again, I'm not saying it doesn't, but I'd be curious to see it without the color.
You're probably used to thinking about color on a map as representing a value.
A heat map, right? Exactly.
And it's not.
Yeah.
This is not. And sometimes you just have to turn your brain off.
Of course.
And look, you know, because that's not what it represents. It's merely a way to read across a row. So here I'm on the red dot. This says that red one is South Dakota, and here's where South Dakota is on the map because it's red. That's all that color is telling you. Now, if you didn't need, excuse me, if you didn't need to see where those states were, you'd still need a way to see where the clusters were or where the ordered values fell.
Totally agree with that. Yeah, absolutely.
So, you know, we just use color to link across the row. That's the only purpose of using the color.
And then how about the you know, having the states that have already been displayed kind of, you know, shown in yellow?
Yeah, sorry, didn't answer that part.
That's okay.
That's an option. I turned that option on because I wanted to show what happened when we got to the middle, that the coasts were still clear.
Yeah.
But it's an option. You don't have to turn it on.
Oh, but you know what? Now that you tell me that, yep, because now I can imagine it without, and you're right. I think it does make it much more clear what's going on.
Let me back up. No, I did have it there. I didn't remember if I had it turned on in that first one. Yeah. So it's useful for looking at accumulation as you go from high to low or vice versa.
Fantastic. Thank you so much.
You're welcome.
Any other questions? In that case, once again, I'd like to really thank Cameron for hosting us. And I cannot thank Linda enough for such an outstanding talk.
Oh, thank you.
Linda had just about an hour to speak, and yet she has so much more to say. You all seemed interested in micromaps. She just spent a few minutes on them. I cannot recommend too highly getting the book, Visualizing Data Patterns with Micromaps. It will go into much more detail. It was written 10 years ago, but I feel that they are not well enough known. If we look at the map we were just talking about, if those maps were not there, if we just had the states and the graphs, I'm not sure that I would have known that the top 5 states were all contiguous and the next 5 states surrounded them. I mean, that pattern jumps at me seeing the maps with the graph. I probably know the states as well as most people who don't know geography too well, but I never would see that just from the state abbreviation. Seeing the maps linked to the graph just shows me this is where it's highest. And look, the second highest is right surrounding those. And you will see many more examples in the book. Linked micromaps are just one type of graph she has. They show comparative micromaps, which she touched on, and other things. And I really recommend the book.
Thank you.
Thank you. Cameron, thank you, Linda, and thank all of you for coming.
Okay.
Again, we will meet in January with Jessica Holman discussing visualizing uncertainty. It's likely to be Thursday, the week of January 4th, but it might be, if anybody has strong feelings about Tuesday, Wednesday, or Thursday, both Cameron and Jessica are free. I thought Thursday would let us recover from the holidays, but we tend to have more conflicts on Thursdays. So it'll be one of those 3 days. Again, thank you all for coming. Thank you, Linda. And see you in January. Stay